Colonel Richard Graham feels the SR-71 snap left, 900 degrees per second, as the right J-58 engine explodes backward, spitting Mach 3 air through its compressor over the Kola Peninsula. The airframe yaws so violently that Graham's inner ear tells him he is rolling inverted, but the attitude indicator shows wings level and the nose tracking left in a flat spin. At 80,000 feet and 2,100 miles per hour, the aircraft is simultaneously too fast to turn and too asymmetric to fly straight. The left engine hammers at full thrust, 18,000 pounds of force shoving the tail right, while the dead right engine generates 0. Graham's hands grip the throttles. The triple redundant computer commands the right throttle forward to restore airflow authority. Graham knows that input will destroy the engine in 4 seconds. He has perhaps 60 seconds before the airframe exceeds its 3.2 G structural limit and begins to disintegrate. The yaw continues. Earlier that morning, Graham and his Reconnaissance Systems Officer, Lieutenant Colonel Bill Okerson, had crossed into Soviet airspace at 80,000 feet, the camera bay hot and recording. Their SR-71, tail number 17980, was 18 minutes into a 34-minute overflight of the Kola Peninsula, photographing submarine pens and airfields near Murmansk. The mission profile allowed no margin for error because there were no divert fields and no second chances. The nearest friendly territory lay 600 nautical miles southwest, across the Barents Sea and Norwegian coastline. At cruise speed, that translated to 16 minutes of flight time if everything worked perfectly. The two Pratt & Whitney J-58 engines, each generating 32,000 pounds of thrust in ramjet mode, burned through fuel at a rate of 8,000 gallons per hour. Graham held the aircraft steady at Mach 3.2, the sweet spot where inlet efficiency peaked and structural loads remained within limits. The J-58 engines operated in ramjet mode, a configuration that existed nowhere else in operational aviation. At speeds above Mach 2.5, the inlet spike positioned 26 inches aft of its full forward position, creating a carefully balanced shock wave at the inlet throat. That shock wave compressed incoming supersonic air to subsonic speeds before it reached the compressor face, decelerating the flow from over 2,000 miles per hour to roughly 400 miles per hour in the space of a few feet. The compression generated temperatures exceeding 800 degrees Fahrenheit, hot enough to glow visibly in certain lighting conditions. Consequently, the spike had to hold position within a tolerance of less than 1 inch, because even a small deviation would cause the shock wave to migrate and the compression ratio to collapse. In ramjet mode, the inlet itself produced more thrust than the turbine section, essentially turning the engine into a controlled supersonic wind tunnel with fuel injection. Each inlet spike moved under the command of pneumatic actuators, a system designed and built in the early 1960s when hydraulic and electronic alternatives remained unproven at extreme temperature and altitude. The actuators responded to signals from the automatic flight control system by bleeding high-pressure air from the engine compressor section, routing it through valves, and extending or retracting the spike along its central rail. The entire sequence required approximately 0.3 of a second from command to mechanical movement, a delay that seemed trivial on the ground, but became critical at Mach 3.2, where aerodynamic conditions changed in 50 milliseconds or less. Consequently, the system lagged behind the physics it was supposed to control, chasing equilibrium rather than maintaining it. Engineers at Lockheed's Skunk Works understood the lag and designed the triple redundant computer to predict spike position changes before they were needed, essentially flying ahead of the aircraft. It worked in all but the most violent transients. The automatic flight control system monitored spike position, throttle angle, and shockwave stability through 3 independent channels, each with its own sensors and logic circuits. If one channel detected an anomaly, the other 2 could outvote it and continue normal operation. If 2 channels agreed, the system assumed the third had failed and ignored its input. The architecture guaranteed that no single failure could cause a loss of control, and it gave pilots confidence that the computer would protect them from errors in judgment or reaction time during high-speed emergencies. However, the system carried an implicit assumption that the computer's solution would always be correct, and that manual pilot input conflicting with the automated command represented a mistake to be overridden. Graham had flown the SR-71 for over 1,000 hours and trusted the automation in almost every scenario. He also knew from conversations with Lockheed test pilots that the automation had never encountered an inlet unstart at Mach 3.2 over hostile territory with no divert options. The mission clock on Graham's instrument panel read 18 minutes since the Soviet border crossing, leaving 16 minutes to exit airspace and reach international waters where tanker support waited. In those 16 minutes, the SR-71 would cover roughly 600 nautical miles, threading a corridor between surface-to-air missile sites and interceptor bases. The timing was not arbitrary. It represented the maximum duration the aircraft could sustain Mach 3.2 cruise before fuel reserves dropped below the safety margin for reaching the tanker. Every second inside Soviet airspace increased the probability of radar tracking, missile launch, or MiG intercept, even though no Soviet system had successfully engaged an SR-71 in operational flight. Graham scanned his instruments in a practiced rhythm: altitude, Mach, exhaust gas temperature, inlet pressure, fuel flow. Every parameter read normal. Okerson in the rear cockpit monitored the reconnaissance systems and watched for ground radar activity. Nothing suggested the violence about to unfold. An inlet unstart begins when the shockwave migrates forward of the inlet throat, a movement that occurs in milliseconds and reverses the entire flow regime inside the engine. Instead of smoothly compressed subsonic air entering the compressor, supersonic air, traveling at over 400 miles per hour, blasts backward through the inlet duct, slamming against the compressor face and stalling the turbine blades. The pressure reversal generates a sound like an explosion, audible even through the pilot's helmet and over the roar of the functioning engine. The flame-holding rings in the combustion section lose their grip on the burning fuel-air mixture, and the engine flames out, thrust dropping from 32,000 pounds to 0 in less than 1 second. Consequently, the aircraft transitions from symmetric flight to violent asymmetric yaw before the pilot's nervous system can register what has happened. The physics operates on a timescale measured in tens of milliseconds, while human reaction time averages 200 milliseconds, and the pneumatic actuators require 300 milliseconds to respond. The pneumatic actuators cannot compensate for an inlet unstart because they respond to conditions that existed 0.3 of a second in the past, while the shock wave has already moved and the pressure regime has already collapsed. When the computer detects the unstart through pressure sensors at the inlet throat, it commands the spike forward to reposition the shock cone and re-establish compression. However, by the time the actuator begins moving the spike, the shock wave has migrated several inches farther forward, and the airflow has reversed direction. Consequently, the actuator chases a target that no longer exists, repositioning the spike for a flow regime that has already changed. At subsonic speeds or even at Mach 2, the lag remains manageable because the rate of change is slow enough for the actuators to catch up. At Mach 3.2, the conditions change 50 times faster than the actuators can move, and the system enters a feedback loop that amplifies the instability rather than damping it. The SR-71 flight manual prescribed a specific restart procedure for inlet unstarts. Maintain or increase throttle position to restore airflow authority. Allow the automatic flight control system to reposition the inlet spike, and wait for the shock wave to stabilize at the throat before attempting engine relight. The procedure derived from decades of subsonic and transonic jet engine experience, where maintaining thrust and airflow prevented compressor stalls from cascading into complete flameouts. At lower speeds, the procedure worked reliably because the engine could windmill through the residual airflow and the compressor could maintain some rotational speed even without combustion. At Mach 3.2 in ramjet mode, however, the physics reversed. Advancing the throttle increased fuel flow into a combustion section that no longer had stable airflow, flooding the engine with unburned fuel and accelerating the compressor stall. Consequently, the standard procedure, designed for subsonic jets, guaranteed destruction of the J-58 turbine in approximately 4 seconds when executed at Mach 3.2. The moment the right engine flames out, the left engine's 32,000 pounds of thrust becomes an off-center force acting 15 feet from the aircraft's centerline, generating a yaw moment that spins the nose left at an accelerating rate. At Mach 3.2, aerodynamic forces amplify the yaw because the airflow over the vertical stabilizer creates a side force that reinforces the rotation rather than damping it. Graham's rudder input, limited to roughly 20 degrees of deflection at high speed to prevent structural overstress, cannot generate enough countermoment to overcome the asymmetric thrust. Consequently, the yaw rate increases from 0 to several hundred degrees per second in less than 3 seconds, and the airframe begins to experience structural loads approaching the 3.2 G design limit. At that limit, titanium spars begin to deform, skin panels buckle, and control linkages bend beyond their elastic range. The clock to structural breakup starts immediately and runs for approximately 60 seconds before permanent damage begins. If the airframe exceeds 4G, even briefly, it will disintegrate in flight. An SR-71 flying on one engine at 80,000 feet cannot maintain altitude because the remaining J-58 produces only enough thrust to overcome drag at Mach 2.8, not Mach 3.2. Consequently, the aircraft begins descending immediately, losing altitude at a rate of roughly 2,000 feet per minute as speed bleeds off and lift decreases. At 70,000 feet, the SR-71 enters the engagement envelope of the Soviet SA-5 surface-to-air missile system, a long-range weapon designed specifically to counter high-altitude reconnaissance aircraft. Below 65,000 feet, shorter-range systems like the SA-2 and SA-3 can reach the aircraft, and below 50,000 feet, even older systems pose a threat. The descent also increases atmospheric density, which raises aerodynamic loads and makes the asymmetric yaw harder to control. Graham's only option for arresting the descent is to restart the dead engine, because attempting to maintain altitude on one engine will bleed airspeed below the minimum controllable speed, and the aircraft will depart controlled flight into a flat spin. There are no ejection seats that can save the crew below 50,000 feet and Mach 2.5. The triple redundant automatic flight control system responds to the Unstart by commanding the right throttle forward, exactly as the flight manual prescribes. When Graham wraps his gloved hand around the throttle and attempts to pull it back toward idle, he feels resistance, because the computer is actively driving the throttle actuator in the opposite direction. The system interprets Graham's input as a pilot-induced error, the kind of mistake that the redundancy was designed to prevent. Consequently, the computer increases servo force on the throttle actuator, fighting Graham's hand with electric motors powered by 3 independent hydraulic circuits. Most pilots would release the throttle and trust the automation because the system has triple redundancy and years of successful operation behind it. However, Graham has heard stories from Lockheed test pilots about edge cases where the computer's solution was wrong and manual override was necessary. He also knows that if he releases the throttle, the computer will advance it, flood the engine with fuel, and destroy the turbine in 4 seconds. He holds the throttle at his desired position and reaches for the autopilot disconnect with his left hand. The right inlet spike pneumatic actuator lags by 0.3 of a second, and in that fraction of time, the shockwave expels forward of the throat, generating a pressure reversal that produces a yaw snap Graham feels through the control stick and seat, a violent lurch left at 900 degrees per second. The aircraft rotates through a quarter turn in 1 second, the nose tracking through 90 degrees while the wings remain level. Graham's vestibular system, evolved to interpret motion in a gravity field at low speeds, cannot distinguish between yaw and roll at 80,000 feet and Mach 3.2. His inner ear tells him the aircraft is rolling inverted, a spatial disorientation error that has killed pilots in similar high-performance jets. Consequently, his instinct is to apply opposite stick to roll wings level, an input that would accelerate the yaw and drive the airframe past the G limit in seconds. However, Graham forces his eyes to the attitude indicator, a gyroscopic instrument that shows the truth. Wings are level. The aircraft is yawing, not rolling. He overrides his vestibular system with instrument data and prepares to counter the yaw. The right J-58 flames out as the reversed supersonic airflow stalls the compressor blades and extinguishes the carefully balanced combustion process in the burner cans. Exhaust gas temperature drops from 1300 degrees Fahrenheit to 600 degrees in less than 2 seconds, and the turbine rotor decelerates as fuel flow continues but combustion stops. The engine becomes a dead weight, producing zero thrust and significant drag, a roughly 4,000-pound penalty hanging off the right side of the fuselage. Simultaneously, the left J-58 remains at full thrust, generating 32,000 pounds of force on the left side of the centerline. The resulting asymmetric condition produces an 18,000-pound differential thrust, because the dead engine not only produces zero thrust, but also creates drag that must be subtracted from the functioning engine's output. Consequently, the yaw moment increases beyond what Graham experienced during training simulations, which assumed the dead engine would windmill and produce some residual thrust. The airframe yaw rate accelerates past 900 degrees per second. The triple redundant automatic flight control system detects the inlet unstart through pressure sensors and immediately commands the right throttle forward to 80%, the position specified in the restart procedure. All 3 independent channels reach the same conclusion within 50 milliseconds of each other, so the system treats the command as validated and correct. The throttle actuator motors engage, driving the lever forward against Graham's grip. The computer's logic is sound for a subsonic jet experiencing a compressor stall. Increase fuel flow and airflow authority to re-establish combustion and prevent the stall from propagating through the engine. However, at Mach 3.2 in ramjet mode, the J-58 operates in a different physics regime, where the inlet produces more thrust than the turbine, and the shockwave position determines whether the engine runs or destroys itself. Advancing the throttle floods the combustion section with fuel, while the airflow remains reversed, washing unburned JP7 through the turbine and into the exhaust nozzle. If Graham releases the throttle and allows the computer's command to execute, the engine will destroy itself in 4 seconds. Graham recognizes that his instruments show yaw, not roll, and that the computer is commanding the wrong throttle input for the flight regime. He wraps his right hand around the right throttle and pulls it back toward idle, feeling the electric servo motors resist his input. His training from Lockheed test pilots, briefings that occurred years ago in classified sessions at Palmdale, taught him that inlet unstarts at extreme Mach required chopping the throttle to idle to allow the shockwave to reposition before attempting relight. That procedure contradicted the flight manual and the computer's programming because it was discovered through test flights that never made it into official doctrine. Consequently, Graham is executing an unauthorized input, one that the triple redundant system interprets as pilot error. He holds the throttle against the servo force for 2 seconds, while his left hand reaches for the autopilot disconnect paddle on the control stick. He presses the paddle, and the autopilot disengage warning tone sounds in his helmet. The servo motors release, and Graham chops the throttle to idle. The moment Graham disengages the autopilot, the flight control system transfers authority from the computer to the pilot's direct inputs. The throttle servo motors go slack, and the stick force feedback changes as the hydraulic actuators switch from computer-commanded to pilot-commanded mode. Graham now has manual control of throttle, stick, and rudder, but he also owns every consequence of his inputs. If he is wrong about the restart procedure, if the Lockheed test pilot's advice was specific to a different configuration or speed regime, he will destroy the engine and force an ejection over the Kola Peninsula. If he is right, he has approximately 10 seconds to reposition the shockwave, restart the engine, and recover symmetric thrust before the airframe exceeds structural limits. The yaw rate continues at several hundred degrees per second. The left engine hammers at full thrust. The altitude reads 78,000 feet and descending. Graham scans the inlet pressure gauges, looking for the indication that the shock wave has collapsed back toward the throat. The gauge needles show reversed flow. He holds the throttle at idle and waits. Graham chops the right throttle to idle, and the fuel flow to the dead J-58 drops from 6,000 pounds per hour to roughly 400 pounds per hour, the minimum necessary to keep the engine's fuel manifolds primed. The combustion section, still flooded with unburned JP-7 from the computer's throttle forward command, stops receiving additional fuel and begins to clear as the residual fuel burns off or drains into the exhaust nozzle. The compressor, no longer driven by combustion gases, decelerates as aerodynamic drag slows the turbine blades. Exhaust gas temperature continues to drop, now reading 500 degrees Fahrenheit, roughly 300 degrees above ambient at 80,000 feet. Consequently, the engine transitions from a failed running state to a completely shut down state, which is the prerequisite for repositioning the inlet shockwave. The reversed supersonic airflow begins to dissipate as the pressure differential across the inlet throat equalizes. Graham watches the inlet pressure gauge for the first sign that the shockwave is collapsing back toward its normal position at the throat. The yaw rate remains high. As the fuel flow drops and the compressor decelerates, the shock wave that expelled forward of the inlet throat begins to collapse back toward its stable position. The physics governing the collapse is straightforward. Without combustion driving the turbine, the engine stops acting as an air pump, and the pressure differential across the inlet throat decreases. The supersonic airflow, no longer blocked by high pressure downstream, decelerates and recompresses as it passes through the inlet duct. Consequently, the shock cone begins to migrate aft, moving from its unstable expelled position back toward the throat where it can compress incoming air to subsonic speeds. The movement occurs over roughly 4 seconds as the aircraft's Mach number bleeds from 3.2 to 2.8 due to the loss of thrust and the increased drag from the dead engine. Graham watches the inlet pressure gauge as the needle swings from the reversed flow indication toward the normal operating range. The pneumatic actuators, no longer chasing a runaway shockwave, begin to respond to the changed pressure regime and prepare to reposition the inlet spike. The pneumatic actuators detect the changed pressure regime through sensors at the inlet throat and command the right inlet spike forward, retracting it approximately 8 inches from its ramjet cruise position. The spike moves along its central rail, driven by high-pressure bleed air from the still-functioning left engine, which supplies pneumatic power to both sides of the aircraft. The retraction repositions the shock cone for a lower Mach number compression ratio, allowing the inlet to capture and compress airflow at Mach 2.8 instead of Mach 3.2. Consequently, the inlet transitions from a failed high-speed configuration to a stable lower-speed configuration, re-establishing the basic aerodynamic function required for engine restart. The movement takes roughly 1.5 seconds, during which Graham monitors the inlet pressure gauge to confirm that the shock wave remains at the throat and does not expel forward again. The gauge needle stabilizes in the normal range. The airflow reversal stops completely, and the 400 mph backward surge through the compressor dissipates as pressure equalizes across the inlet duct. The 400 mph backward compressor surge? The violent reversed airflow that stalled the turbine blades and caused the flameout? Dissipates as the pressure across the inlet duct equalizes. The compressor blades, which had been hammered by supersonic air traveling in the wrong direction, slow to an idle windmill speed, driven only by the residual airflow passing through the inlet. The titanium blades, designed to withstand temperatures exceeding 1,000 degrees and rotational speeds above 10,000 revolutions per minute, have survived the surge without permanent deformation because Graham's throttle chop stopped fuel flow before the unburned JP-7 could ignite in the turbine section and melt the blade roots. Consequently, the engine remains mechanically intact and capable of restart, although it is still producing zero thrust and the aircraft continues to yaw left under asymmetric thrust from the functioning left J-58. Graham advances the right throttle to 60%. the prescribed position for in-flight engine start, and watches the fuel flow gauge as JP7 begins flowing to the combustion section once more. Graham advances the right throttle to 60%, and the fuel control unit responds by increasing JP7 flow from 400 pounds per hour to roughly 3,000 pounds per hour. The fuel flows through manifolds and injector nozzles into the combustion cans, where it mixes with the now stable subsonic airflow entering from the compressor section. The fuel injectors spray a fine mist of JP7 that vaporizes in the hot airflow, creating a flammable fuel-air mixture. However, the mixture will not ignite spontaneously because the exhaust gas temperature has dropped below the auto-ignition point for JP7, which is formulated to be exceptionally stable at high temperatures to prevent accidental combustion in the aircraft's fuel tanks during Mach 3 cruise. Consequently, the engine requires an ignition source to initiate combustion, and that source comes from triethylborane cartridges, a pyrophoric chemical that ignites on contact with air. Graham presses the engine start button, and the TEB system injects a slug of the chemical into the combustion cans, where it ignites instantly and lights off the JP7 mixture. The triethylborane ignites the JP7 fuel-air mixture in the combustion cans, and flame propagates through the burner section as the fuel injectors continue spraying vaporized JP7 into the hot airflow. Exhaust gas temperature begins to rise, climbing from 500 degrees Fahrenheit toward 900 degrees as combustion reestablishes. The hot exhaust gases accelerate through the turbine section, driving the turbine blades and increasing their rotational speed from idle windmill to powered rotation. The turbine, now driven by combustion gases rather than residual airflow, accelerates the compressor blades at the front of the engine, which in turn increase the mass flow and pressure of air entering the combustion section. Consequently, the engine enters a self-sustaining cycle where combustion drives the turbine drives the compressor, and the compressor supplies air to maintain combustion. The J58 transitions from a dead engine to a running engine over approximately 6 seconds as turbine speed climbs toward the minimum self-sustaining RPM. Graham watches the exhaust gas temperature gauge climb and the RPM indicator accelerate. As the turbine RPM climbs and the compressor accelerates, the inlet spike pneumatic actuators begin repositioning the spike aft toward the ramjet cruise position. The spike moves roughly 6 inches aft over 3 seconds, repositioning the shock cone to capture and compress airflow at the increasing Mach number as the aircraft accelerates from Mach 2.8 back toward Mach 3. The inlet transitions from subsonic compression mode, where the compressor does most of the work, to ramjet mode, where the inlet shockwave does most of the compression, and the turbine primarily serves to drive the compressor and control fuel flow. At Mach 2.9, the J58 achieves full ramjet operation, producing over 30,000 pounds of thrust, as the inlet contributes more pressure rise than the compressor. Consequently, the right engine restores symmetric thrust, and the 18,000-pound differential force that was yawing the aircraft left drops to near zero. Graham feels the yaw rate decay through the control stick as aerodynamic forces rebalance and the aircraft returns to coordinated flight. The structural stress gauge reads 1.8 G, well below the 3.2 G red line. With symmetric thrust restored, Graham applies differential rudder to damp the residual yaw oscillation that continues at roughly 200 degrees per second. The vertical stabilizer, spanning over 12 feet in height and located 30 feet aft of the center of gravity, generates a side force when Graham deflects the rudder, creating a yaw moment that opposes the oscillation. At Mach 2.9 and 72,000 feet, the rudder's effectiveness is reduced compared to lower speeds and denser air, so Graham must apply larger deflections and hold them longer to achieve the desired damping effect. He feeds in right rudder as the nose swings left, then releases it as the yaw rate decreases, then applies left rudder as the nose begins swinging right in the opposite direction. The oscillation amplitude decreases with each cycle, decaying from 200 degrees per second to 100 degrees per second to 50 degrees per second over roughly 12 seconds. Consequently, the aircraft transitions from violent yaw oscillation to minor heading corrections to stable flight on a constant heading. The structural stress gauge stabilizes at 1.8 G. Graham's instrument scan confirms both engines producing thrust, altitude stabilizing, Mach number climbing. For 12 seconds after Graham restarts the right engine and begins damping the yaw oscillation, the outcome remains uncertain. The airframe structural stress oscillates between 1.8 G and 2.9 G as the yaw rate fluctuates and aerodynamic loads vary with each rudder input. The 3.2 G red line remains only 0.3 of a G above the peak stress, a margin equivalent to roughly 15 degrees of additional yaw or one mistimed rudder input. If Graham over-controls, applying too much rudder deflection or holding it too long, he can drive the stress past the red line and initiate structural failure. If he under-controls, the yaw oscillation will not damp and will eventually couple with roll or pitch oscillations, creating a complex departure from controlled flight that cannot be recovered at this altitude and speed. Consequently, every rudder input must be precisely timed and precisely removed, and Graham's hands and feet must execute control movements he has practiced in simulators, but never at Mach 2.9 over Soviet territory with a recently restarted engine. The margin between recovery and breakup exists in fractions of a second and degrees of control deflection. While Graham damps the yaw oscillation, Soviet ground-based radar at air defense sites along the Kola Peninsula track the SR-71's erratic flight path. The aircraft's sudden deceleration from Mach 3.2 to Mach 2.8 and altitude loss from 80,000 feet to 72,000 feet appear on radar screens as a possible malfunction or battle damage, making the Blackbird a more vulnerable target than usual. An SA-5 missile battery at Murmansk, positioned to defend the Soviet Northern Fleet submarine bases, achieves a fire control solution as the SR-71's altitude drops within the upper engagement envelope of the system. The SA-5, designed specifically to counter high-altitude reconnaissance aircraft, can reach targets up to 100,000 feet and has a maximum speed exceeding Mach 3.5 in its boost phase. However, the missile's guidance radar requires the target to maintain a predictable flight path for several seconds to establish a firing solution. Graham's yaw oscillations and continuously changing heading produce enough variance that the radar cannot achieve a stable lock. The fire control system cycles between lock and search modes, unable to commit to launch. If the SR-71 stabilizes on a constant heading for more than 5 seconds, the SA-5 battery will achieve firing parameters. Graham advances the right throttle from 60% to 80% to accelerate the aircraft back toward cruise speed and climb out of the SA-5 engagement envelope. The right J-58 responds by increasing fuel flow and turbine RPM, and thrust climbs from roughly 25,000 pounds to 29,000 pounds. The left engine remains at 100%, producing its full 32,000 pounds, so the aircraft still experiences a slight thrust differential, but the asymmetry has decreased from 18,000 pounds to 3,000 pounds. Consequently, the yaw moment decreases and the rudder inputs required to maintain heading become smaller and less frequent. The aircraft accelerates from Mach 2.9 toward Mach 3.1, and the rate of climb increases from 0 to roughly 1,000 feet per minute. Graham watches the altitude readout tick upward: 73,000 feet, 74,000, 75,000. The structural stress gauge stabilizes at 1.8 G with no oscillation. The yaw rate decays to less than 10 degrees per second, a value within the normal flight control system's authority to manage without pilot input. The yaw oscillation damps completely as the aircraft reaches Mach 3.1 and 76,000 feet. The vertical stabilizer's aerodynamic damping, combined with Graham's precisely timed rudder inputs, dissipates the last remnants of the rotational energy imparted by the initial asymmetric thrust condition. The aircraft's nose tracks a constant heading, and the yaw rate drops to 0 degrees per second. Graham releases rudder pressure, and allows the flight control system to maintain heading through small, automated rudder adjustments. The structural stress gauge reads 1.6 G, a normal value for Mach 3 cruise at this altitude and gross weight. Consequently, the aircraft transitions from emergency recovery to normal supersonic cruise, and the immediate threat of structural breakup disappears. Graham scans his instruments. Both engines producing full thrust. Inlet spikes at ramjet position. Exhaust gas temperatures normal. Fuel flow balanced. Okerson, who has been silent in the rear cockpit during the entire emergency, keys the intercom and asks for status. Graham replies that both engines are running and they are continuing the mission. The SA-5 missile battery's fire control radar loses its tracking solution as the SR-71 accelerates through Mach 3.1 and climbs back to 78,000 feet. The aircraft's increasing speed and altitude take it outside the stable tracking parameters required for missile launch, and the radar system returns to search mode rather than maintaining a lock on a target that is rapidly increasing range and altitude. The Soviet air defense operators watch the radar return accelerate and climb, confirming that the Blackbird has recovered from whatever malfunction caused the temporary deceleration and altitude loss. No missile is launched because by the time the fire control solution would have been achieved, the SR-71 would have been outside the missile's kinematic reach. Consequently, the external threat dissipates at the same moment the internal structural threat is resolved. Graham is unaware of the SA-5 radar activity because the SR-71's radar warning receiver is optimized for detecting fighter intercept radars and missile guidance radars, not ground-based search and fire control systems. He continues the mission, unaware how close the Soviet missile battery came to achieving a firing solution. Graham and Okerson exit Soviet airspace 11 minutes later, crossing the Barents Sea coastline and entering international airspace over Norwegian territorial waters. Both J-58 engines remain at full thrust, producing a combined 64,000 pounds and maintaining Mach 3.2 at 80,000 feet. The reconnaissance cameras in the camera bay have continued operating throughout the emergency, recording images of Soviet submarine facilities and airfields, even while Graham fought the yaw oscillation and restarted the engine. The mission profile is complete, the film canisters are full, and no secondary unstarts have occurred. Graham advances both throttles to military power, reducing fuel consumption for the transit to the tanker rendezvous point over the Norwegian Sea. He reviews the emergency in his mind, cataloging the sequence of events for the post-flight debrief. Inlet unstart, throttle to idle, shockwave repositioning, engine relight, yaw damping, recovery. The entire sequence from unstart to stable flight lasted approximately 45 seconds, during which the aircraft lost 8,000 feet of altitude and decelerated by 0.4 Mach. He knows the flight data recorder captured every input and parameter. Graham lands the SR-71 at Royal Air Force Mildenhall in England 90 minutes later, touching down on the runway at 170 knots and deploying the drag chute to decelerate the titanium airframe. The post-flight inspection begins immediately, with Lockheed engineers and Air Force maintenance technicians examining the right J-58 engine for signs of damage from the inlet unstart and restart cycle. They remove the inlet spike, inspect the pneumatic actuators, and borescope the compressor section, looking for deformed turbine blades, burned combustion can liners, or cracks in the turbine disc. The inspection reveals no structural damage and no deformation beyond normal wear limits. The engine sustained the unstart, the reversed airflow, and the high-speed restart without failure. Consequently, the aircraft is declared airworthy and returned to operational status within 24 hours. However, the flight data recorder download reveals something that concerns the Lockheed engineers. Graham's throttle input during the restart violated the automated restart protocol by 8 seconds, chopping the throttle to idle when the computer commanded throttle forward. By all measures, the pilot overrode the triple redundant system and executed an unauthorized procedure. Lockheed engineers download the flight data recorder and analyze the inlet unstart sequence, plotting throttle position, inlet spike position, shockwave pressure, and structural G loading on a synchronized timeline. The data shows that Graham's manual throttle chop to idle occurred 8 seconds before the automated restart protocol would have commanded the same input, after first attempting to re-establish airflow by advancing the throttle. The engineers recognized that if Graham had allowed the automated sequence to execute, the engine would have been flooded with unburned fuel for those 8 seconds, and the probability of successful restart would have dropped significantly. However, they also recognized that Graham's input contradicted the flight manual, the computer's programming, and the training doctrine for inlet unstarts. Consequently, they face a difficult question: whether to classify Graham's action as a procedural violation that happened to work, or as the correct response to a flight regime that the automated system was never designed to handle. According to the Accident Investigation Board's later review, Graham's manual restart sequence became the template for a revised emergency procedure. Graham's manual restart sequence: throttle to idle, allow shockwave to reposition, graduated throttle advance to 60%, TEB ignition, and progressive throttle increase to cruise power, becomes the official SR-71 emergency procedure for inlet unstarts at speeds above Mach 3. The procedure is codified in a revision to the flight manual and incorporated into SR-71 training syllabi at Beale Air Force Base in California, where all Blackbird crews receive their qualification training. The revised procedure explicitly authorizes pilots to override the automatic flight control system during high-speed inlet unstarts and execute manual throttle inputs that contradict the computer's commands. Consequently, the doctrine shifts from computer-first authority to pilot-first authority in specific high-speed edge cases where the automated system's logic, though sound for subsonic and transonic jets, does not match the physics of ramjet operation at Mach 3. The change represents a significant philosophical shift because it acknowledges that the triple redundant computer, despite its sophistication and reliability, cannot anticipate all failure modes at the extreme edge of the SR-71's flight envelope. The SR-71 Blackbird fleet logs 37 subsequent inlet unstarts between Graham's incident and the aircraft's retirement in 1998, spanning roughly 14 years of continued operational flying. Of those 37 unstarts, 36 are recovered using Graham's manual override technique, with pilots chopping throttle to idle despite computer commands to advance throttle, allowing the shockwave to reposition, and executing graduated engine relights. The single unstart that does not fully recover occurs over Libya in 1987, when the pilot follows the automated restart protocol and the resulting structural overstress forces an emergency descent and mission abort, although the aircraft recovers and lands safely. Consequently, Graham's unauthorized procedure demonstrates a success rate exceeding 97% and becomes the standard response for high-speed inlet instability throughout the Blackbird's operational life. The fleet completes its service with 0 losses attributable to inlet unstarts, a record that validates the manual override doctrine and Graham's decision to trust his training from Lockheed test pilots over the triple redundant computer's commands. The single SR-71 inlet unstart that does not fully recover using Graham's procedure occurs during a reconnaissance mission over Libya in 1987. The pilot experiences a right engine unstart at Mach 3.1 and 79,000 feet, nearly identical conditions to Graham's emergency. However, this pilot follows the automated restart protocol for the first 4 seconds before switching to manual override, a delay that allows the computer to advance the throttle and flood the combustion section with unburned fuel. When the pilot finally chops the throttle to idle, the shockwave has migrated farther forward, and the engine's fuel manifolds are saturated with JP7, creating a more severe restart condition. The engine relights successfully, but the delay causes greater yaw oscillation amplitude and higher structural G loading, with the airframe briefly exceeding 3G before the pilot damps the oscillation. The structural overstress does not cause permanent damage, but it triggers an automatic flight envelope protection warning that requires the pilot to abort the mission and return to base. Consequently, the incident reinforces the doctrine that manual override must be executed immediately during high-speed unstarts, with no delay for the automated system to attempt its procedure first. The SR-71 program's operational history reveals that the triple redundant automatic flight control system, despite its sophistication and reliability, operates under assumptions that do not hold at the extreme edges of the aircraft's performance envelope. The computer's restart logic assumes that advancing the throttle will restore airflow authority and allow the inlet spike to reposition, a principle that works correctly for subsonic jets where the compressor dominates engine performance. At Mach 3.2 in ramjet mode, however, the inlet dominates performance, and the shockwave position determines whether the engine runs or destroys itself, reversing the cause and effect relationship the computer was programmed to enforce. Consequently, the computer's solution is not wrong in an absolute sense, but rather inapplicable to the specific physics regime where the SR-71 operates at its highest speeds. The recognition leads to a broader understanding within the aerospace community that automation, no matter how redundant or sophisticated, cannot substitute for human judgment in genuinely novel situations where the underlying assumptions of the automated system do not match physical reality. Graham's decision to override the computer becomes a case study in pilot authority and situational awareness. The SR-71 Blackbird fleet retires from operational service in 1998 after 33 years of reconnaissance missions over denied territory, having completed thousands of sorties without a single loss attributable to Inlet Unstarts. The zero-loss record represents a remarkable safety achievement for an aircraft operating at speeds and altitudes where mechanical failures can escalate to catastrophic consequences in seconds. The record is built on multiple layers of engineering excellence, pilot training, and procedural discipline, but Graham's contribution, proving that manual override of the automated system was not only possible, but necessary at Mach 3, stands as a critical element in that safety architecture. When the last SR-71 makes its final flight to the Smithsonian National Air and Space Museum, the aircraft carries with it the legacy of Graham's 45-second emergency over the Kola Peninsula, an event that defined the limits of automation and the essential role of human judgment at the edges of human flight. The throttle chop that Graham executed in defiance of the computer became the procedure that saved 36 subsequent crews. Colonel Richard Graham's decision to override the triple redundant computer during an Inlet Unstart at Mach 3.2 over the Kola Peninsula demonstrates a principle that extends beyond the SR-71 program: that human operators remain essential at the edges of engineered systems, where the assumptions embedded in automation confront physical realities the designers never anticipated. The computer commanded throttle forward because that is what subsonic jet doctrine prescribed, and the logic was sound for the environments where it had been validated. Graham recognized that the logic did not apply at 80,000 feet and Mach 3.2 over Soviet territory, and he trusted his training from Lockheed test pilots over the triple redundant systems authority. His unauthorized throttle chop saved the aircraft, saved the mission, and established the procedure that would protect 36 subsequent crews from the same failure mode. The legacy is not that automation is unreliable, but rather that automation, like any engineered system, operates within boundaries, and human judgment remains necessary to recognize when those boundaries have been exceeded.